Hello, this work was presented at Front-End Sheffield in November 24, and I'm grateful for the opportunity. There will also be a workshop in about a month's time, at the time I'm recording this video, in January 25. More information in the description of the video. I'm working on programming systems and making them available. Most people would tell you that there is a kind of trade-off. Either something is very powerful, but then it's not easy to use at all. Programming languages might belong to that. Or else it's easy to use, but at the same time you cannot do very much with it. It's not very powerful. But a lot of developers in the work of user experience would say, no, that's not true. Take this little thing, for example. That is the first ever mouse invented by Doug Engelbart, a remarkably creative man who showed in his software and with many other tools that you can create things that are easier to use and also more powerful. Even better, you can actually do it in systematic, in organized ways by studying the problem. So when it comes to development, we've got plenty of examples of that, starting with maybe things like Logo, which was given to children in the 1970s when people did not imagine that a computer was something you'd put in the hands of a child, or spreadsheets that made it so much easier to create and develop by anyone working in business, all the way to things like Scratch, which is a computer programming language developed to be used by children. With it, 8-year-old children can actually do things that we thought could only be done by specialists only 3 or 4 years before. One way of understanding end-user development is something like this. When we develop software, we have this thing that we call computer code, and of course we're going to get a visual end result, but we try to progress at both ends of this problem. So we can make the code easier to show, manipulate, make it more editable in more straightforward ways. And we can also represent and manipulate the result. That is, if we expect a result to be, some kind of window with buttons in it and this sort of thing, then we would want to draw that and not type up how big the button is in numbers inside code. So it's a use of both of these sorts of things to create something where the user experience of developing is much more straightforward. Now, there's been a lot of progress, but mostly in areas of development that do not involve the enormous amount of data that we now manipulate. And I work with data. In data, the problem has become urgent. We have systems that present data or facilitate exploitation of data, and we need more accessible ways for people to actually understand where their data is coming from and manipulate it. There are representations of how we handle data. There has been for a long time. One of the easiest things that people have done is to say, well, my data is a piece of information arriving into a box. And a box is some calculation that will produce a result. The result comes out at the other end. And we can create a workflow tool that will transform the data and then take the result and transform it into something else, and so on and so forth. And there are many tools that actually offer to do this. This thing here is called LabVIEW, and it's been commercially successful and it's been around for quite a long time. Yahoo Pipes was quite well known and popular for a period, but it cost Yahoo a lot of money to maintain it, so it's not available anymore. These two are interesting. This is a language called Luna, which is available as open source. And this picture is taken from a tool called Orange Data Mining, which is used by scientists when they'd rather be focusing on the work they're doing with the data and less so on the programming. The last one there is an image of a tool called Ecus, which is used along with spreadsheets and has been developed at Sheffield Hallam University by my supervisors. I should always be nice to my supervisors when I present something. In a work in my research, I developed this tool called open piping. And at first I was treating it like an engineering problem. I segmented separate elements, each of which is open source. But I quickly found out that the real problem was somewhere else. Here is an example of what this looks like. It appears simple enough. There's a lot of detail in actually moving boxes and jingling them about on the screen to be able to link things and so on. And it really is that poor user experience that makes all the difference. Here's an example of using the language. FizzBuzz is initially a children's educational game to make them count 1, 2, 3, 4, 5, 6, except that when the number is a multiple of 3 or of 5, instead we should be saying fizz or buzz. And when a multiple of buzz, FizzBuzz, counting 1, 2, fizz, 4, buzz, fizz. This piece of the problem takes one number and it works out whether the result should be counting the number or else saying fizz or else saying buzz or else saying FizzBuzz. And here the visual doesn't really help. So to understand this better, we took to some theory. Among others, there's this system called physics of notation that looks into the design space that we have got to get this right, and use that to try and draw alternative ways to represent things. Like, for example, this, to use more of the perception space instead of having grey lines and boxes all the time, to represent as much as possible of the concepts the end user is handling. The type of information that we are processing is important, but that wasn't really that helpful. We still end up with a very complicated representation that is difficult to manipulate. Another theory is called cognitive dimensions. Cognitive dimensions doesn't attempt so much to give definite guidelines. Instead, it gives tools to observe what is happening and make our own choices. It has helped trying to understand what is happening. Quite clearly, what's wrong with these things is there's just too many blocks on the screen. And there would be even more, of course, as soon as the problem gets a bit bigger, and it's difficult to follow what is happening. There also is a difficulty in zooming out of the detail. If you've got too many blocks on the screen, you want to actually be able to ignore some of them, or maybe step away from some of the information that we have got. And there is too much of what we could call an abstraction gradient. That is, to move from detailed presentation to a more abstract one. It's too hard. But there is a worse one. Some of the time, we have to do things like these. I want to take every number to calculate the square of each one of them. And at that moment, this isn't an operation I'm carrying out. It's information that I'm giving to map. Map is going to do the 1, then the square of 1, then of 2, then of 3, then of 4. It's information that I'm giving to map so that we can carry out the information later. So is this thing a box, a function that needs to be run? Or is it a wire, a piece of information that is handed to map? The drawing is not helping us anymore. In the 80s, Etienne Wenger studied intelligent tutoring systems. Intelligent as it was then, it was not at all the same sort of thing as ChatGPT. At the time, he showed that you wanted to line up three things. You wanted your front end, your interface, to look like what people are thinking of, and also to look like what was going to happen inside the system. And if you line up these things, it works a lot better. Cognitive dimensions and physics of notations also have the same idea but different names. The notion is important. In a way, what limits the data flow is the fact that because it is abstraction hard, we struggle to actually step away from representations like these that are too detailed, so it's not concise. But also, we struggle to have representations that correspond to what we really think of, which is not so detailed, and step away in things that are meaningful for us. Both of these things affect usability and learnability. We need better notations for more abstract representations so that we can move to something that is more compact and comes closer to how we think of the problem. To be able to find that, we can go through lots and lots of drafting and drawing and attempting different solutions, but that's going to be endless. Instead, I took an approach that is called a Delphi study, to gather a group of experts and ask them their view, try to build a consensus among them by showing each individual expert the views of the others and get them to converge on some ideas. So we used the open piping software, which is very basic, and we kept it under-designed. That gave a starting point for the examples, but also it was clearly not complete enough, so it left a lot of room to let participants propose their own ideas. There were a lot of propositions. Here is one that I think is clever. So you could actually represent the inputs to a function not by a name but by a shape, and then reproduce that shape in the visual of the function itself. Or here is something interesting that makes the comparison with tools like Scratch. The connection that is here a long line that can be a little difficult to trace could actually be something as small as a puzzle shape. And there were a lot of other suggestions, some more like drone, some made in English. Though the worst part of it all was what we call anonymous functions, which are about this idea that we are producing a block here, calculating a square, but we are passing it as if it was data, and that creates a lot of confusion. So that was the worst element of our work, which is this confusion when the idea that a block and a wire are not the same thing becomes unhelpful. From there, we got several pointers to useful elements of solution. The first one is not a big surprise. There has to be a system of types. So here is how we could represent key types of information. There was no agreement on how you show them, just that we should. Are there shapes? Are there colors to represent different types? Here, the suggestion I gave the panel is to use both. Another important insight is that we don't have to make a binary choice between certain things. So one is, for example, do I use a long connector like here? Or do we use a short one as it is here? Well, that doesn't matter. Or do I name a variable as we do here? The named variable becomes a block. Or do we use a connector? Again, it doesn't matter much. There were a lot of remarks that led to identifying how we can have fewer blocks. An irritating one is choosing between different solutions when you have a conditional. It should be possible to actually do something like, if this happens, do this. Otherwise, if this other thing happens, then do this. Otherwise, and something that extends in that kind of way to have multiple conditions, avoid having lots of separate blocks for this. Another interesting one is grouping blocks that process the same thing, so that when you have information and it has to be processed in two different ways, you can join these two blocks together and process your input in the different ways that you need. It helps to place functions inside what we would call frames. So it doesn't matter if a function has a name or not. The trick here is to not make anonymous functions look special. Here is a function here that does not have a name. It takes a number multiplied by itself. So no, we recognize what it is doing, but it looks very much the same as another function here. Something that remains unresolved, or what you do with the operations you're carrying out, mean that this data is really a block, is really an operation that has to be passed around. And there's a concept that has to be shown well by the representation, and that remains confusing. So to understand this better, I would like to work with volunteers in a workshop. We will run this on the 9th of January in Sheffield Hallam University. The details are in the description, as well as a registration form if you would like to confirm your volunteer. Thank you very much for listening to this till the end. I hope you have enjoyed this, and to see some of you in a workshop. Bye.